the story works. Fine until you run it backward. Somewhere out there, right now, a star is falling into a black hole, and it will never finish. Not because it's moving too slowly, because past a certain point, to anyone watching from far enough away, it stops moving at all. It just keeps fading, the way a voice fades before you catch the last word of it. It never lands. It never crosses. It just gets quieter and redder and further away forever, without ever actually leaving. Anyone who has ever watched something disappear slowly, a tail light shrinking on a highway, a signal dropping out mid-sentence, as name spoken for the last time without either of you knowing it was the last time, already understands this, even without a word for it. Here's the part that doesn't sit right once you notice it. Take that entire scene, the star, the falling, the fading, and play it backward. Every equation that describes the forward version describes the reverse version just as well. Same gravity, same curvature, same math, run the other direction. Nothing in the physics objects. And yet something falls into a black hole. Nothing has ever been seen coming out of one the same way. That gap between what the equations allow and what the universe actually seems to do is where this chapter lives. It isn't a contradiction exactly. It's stranger than that. It's a door that the math insists is there, standing open in a wall nobody has ever walked through. Physicists have a name for the thing on the other side of that reversal. They call it a white hole, and once you understand what it would have to be, you start to understand why it has never once been caught in the act of existing, and why, according to the physics itself, it may not be able to. We'll get there slowly. That's the only way this one holds together. Start with the asymmetry itself, because it's easy to nod along at time reversal without letting it actually land. Almost nothing in physics, at the level of a single equation, cares which way time runs. Drop a ball, and the equation that describes its fall also describes with equal confidence a ball rising off the ground and landing gently in your hand. Newton's laws don't have an arrow built into them. Neither does Maxwell's description of light, nor Einstein's description of gravity. Run any of them backward on paper, and nothing breaks. The pen doesn't hesitate. What breaks, what always breaks, is everything else. A dropped glass does not reassemble itself off the floor. Smoke does not gather itself back into a snuffed candle. Cream does not separate itself back out of coffee. None of those violate any fundamental law when you write them out. They're just staggeringly, cosmically unlikely to happen in that order, because there are vastly more ways for a glass to be scattered than whole, and the universe statistically tends toward the direction with more ways to happen. That's the real reason time seems to have a direction at all, not because the laws demand it, but because probability does, once you have enough moving pieces. A falling star is not a coffee cup. It's closer to the single ball case, clean, symmetric, describable, with a small number of equations that don't obviously care about direction. And that's exactly what makes the black hole asymmetry so unsettling. This isn't a case where you'd expect time reversal to fail. It's a case where, by every reasonable expectation set by the rest of physics, it shouldn't fail, and does anyway completely without exception, everywhere astronomers have ever looked. Picture it directly. A distant observer. You, if you had a strong enough telescope and an unreasonable amount of patience, watch as a clump of matter drift toward the boundary of a black hole. As it approaches, something happens to the light it's giving off. The light climbing back out toward you has to fight the same gravity pulling the matter in, and fighting gravity costs energy. Photons don't slow down to pay that cost. They can't. Light always moves at the same speed, so instead they stretch. Their wavelength lengthens. Red light drifts toward the deep red, then past what your eyes would even register as red, out into infrared, then further into wavelengths no eye was ever built to catch. At the same time, something happens to your sense of when things are occurring. Every tick of a clock falling toward the boundary takes longer to reach you than the tick before it, by a margin that grows and grows. A clock ticking once per second at a safe distance appears, from your vantage point, to tick once every 10 seconds as it nears the boundary, then once a minute, then once a year. The intervals stretch out the same way the light stretches out, both effects born from the identical cause. Gravity is warping not just space near that boundary, but the rate at which time itself seems to pass there, at least as far as anyone outside can tell. Put those two effects together and you get the fading. Not a fade to black in the cinematic sense all at once, but a fade that never actually completes dimmer and redder and slower, asymptotically, forever, technically never quite reaching true darkness even after the light has become too faint and too stretched for any instrument ever built or ever conceivable to register it. For all practical purposes it disappears. For all mathematical purposes it is still, this very instant, infinitesimally still arriving. That's the forward story, and it is on its own already strange enough to fill a chapter. But it isn't the strange part this book is about. The strange part shows up when you take that entire sequence, object approaching, light stretching, clock slowing, the long fade toward a boundary it never quite reaches, and run the tape the other way. Reverse the fading, and you get brightening. Reverse the approach, and you get departure, a clump of matter receding from a boundary rather than sinking toward one, its light climbing from deep red back up toward visible wavelengths as it goes, its clock speeding back up from a near standstill to a normal tick. Reverse the whole scene, in other words, and you get something that looks like an object being launched outward from a boundary that nothing can otherwise cross, gaining speed and brightness as it clears the danger zone. Nothing in the equations complains about this. That's the part worth sitting with. It's not that the reversed scenario is permitted with caveats, the way a physicist might grudgingly allow an unlikely but technically legal outcome. It's permitted with exactly the same confidence, the same mathematical cleanliness, as the forward version. Whatever solved the forward problem solves the backward problem too, because it's the same solution. Just read in the other direction. And yet the sky has never shown us the reversed version. Every observed case of a black hole, thousands of them now catalogued across X-ray binaries, galactic centers, gravitational wave events, imaged directly by the Event Horizon Telescope, behaves exactly like the forward story and never once like the reverse. Matter falls in. Matter does not spontaneously launch itself back out, brightening from the boundary of one. If the equations are agnostic about direction, why is the universe so relentlessly, so completely, so boringly one-directional about it? That question is the hinge this entire book turns on. Not, is a white hole mathematically possible? It clearly is, and we'll spend the next chapter proving exactly where in the equations it lives. The real question is why something the math treats as an equal, symmetric partner to the black hole has never shown up, not once, not anywhere, in a universe old enough and large enough that never is supposed to mean something. There's a temptation, hearing this for the first time, to assume the answer is simple, that white holes are just rare, the way a particular arrangement of shuffled cards is rare but not impossible, and we simply haven't looked long enough or hard enough to catch one. That temptation is worth naming early, because it's wrong, and it's wrong in an interesting way. This isn't a story about rarity. Rarity would mean the odds are long but non-zero, that somewhere in a sufficiently large universe, sufficiently patient observation would eventually turn one up. What actually seems to be true is closer to a structural impossibility. Not that white holes are hard to find, but that white holes are hard to keep, in a way that has almost nothing to do with how often the universe tries to make one, and everything to do with what happens the instant one exists. That distinction between something being rare and something being unsurvivable is the whole shape of the argument to come. Every chapter after this one is really circling the same question from a different angle. What specifically kills a white hole so fast, so completely, that even asking, how often does the universe make one, turns out to be the wrong question entirely? Before any of that, though, the object itself needs defining properly, because the reverse of a black hole is a description, not a definition, and it hides more than it reveals. To actually understand what would have to be true for a white hole to exist, and therefore what has to go wrong for it not to, the story has to go back to where the whole idea started. Not in a telescope, not in an observation, but in a piece of paper worked out by a soldier on the Russian front, less than 2 months after Einstein published the field equations themselves. There's a second room in the same equation. Start far from the object itself, further than any telescope has ever needed to look, at the level of the equation instead of the sky. In 1916, a physicist named Carl Schwarzschild worked out the first exact solution to Einstein's field equations, describing the space around a single non-rotating mass. It's the equation used, in some form, in every black hole calculation done since. What almost nobody notices on a first pass is that the solution doesn't describe one region of space. It describes 4. 2 of those regions get all the attention. One is the ordinary universe outside the object, the part we can observe. The other is the interior of a black hole, the region past the horizon where everything, including light, is pulled inward toward the center. That's the version taught in classrooms, drawn in diagrams, referenced in every documentary about the edge of the universe. The other 2 regions sit quietly underneath, present in the math from the very beginning, unused for decades. One is a separate, causally disconnected universe, a parallel exterior that the equations permit but that nothing in our observable universe can ever reach. And the 4th is the mirror image of the black hole interior, a region where the direction of everything is flipped, where the horizon only allows outward motion, where instead of a future ending in a center, there is a past beginning at one. That 4th region is the white hole. It was sitting at the mathematics before anyone had a name for it, the way a room can exist in a house's original blueprint for years before anyone opens the door and asks what it's for. Nobody added it later to make a strange idea work. It was there in 1916. It just took the field several decades to take it seriously enough to ask what it would mean if it were real. What it would mean, it turns out, is a great deal, and almost none of it is comfortable. It's worth pausing on the circumstances of that original 1916 discovery, because they say something about how strange this piece of physics has been from the very start. Karl Schwarzschild wasn't sitting in a university office with the luxury of unlimited time. He was serving in the German army, calculating artillery trajectories on the Eastern Front, when he read Einstein's newly published field equations, 10 coupled non-linear differential equations that Einstein himself doubted anyone would solve exactly any time soon, and apparently in his spare time between military duties, found an exact solution for the simplest possible case: a single, perfectly spherical, non-rotating mass sitting alone in otherwise empty space. He mailed the result to Einstein, who was reportedly astonished that anyone had found a clean answer so quickly. Schwarzschild died a few months later, of a rare autoimmune skin disease contracted at the front, never learning what his solution would eventually be understood to contain. For decades, the solution was treated as a strictly local description, accurate outside a star or a planet, useless and possibly meaningless at very small radii, where the equations seemed to blow up into infinities that nobody quite knew what to do with. The now famous boundary, sitting at a specific radius determined entirely by the mass of the object, what's now called the Schwarzschild radius, looked, on the original coordinate system Schwarzschild used, like a genuine catastrophe, a place where the math simply stopped making sense, where terms divided by zero, where the equations seemed to be screaming that something had gone wrong with the universe itself at that exact distance from the centre. It took until the late 1950s and early 1960s for physicists to realise that the apparent catastrophe wasn't a flaw in physics. It was a flaw in the coordinates. The equations weren't breaking down at that boundary. The description was breaking down, the way a globe's flat map inevitably tears or distorts near the poles, even though nothing strange is actually happening to the Earth there. Choose a different coordinate system, one that doesn't try to force the geometry into an ill-suited grid, and the boundary stops looking like an edge of the universe and starts looking like exactly what it is: a horizon, a one-way membrane, perfectly smooth and unremarkable to anyone crossing it, even though it looks catastrophic from outside. The physicist most responsible for untangling this was Martin Kruskal. Working with the Hungarian physicist George Sekeres, arriving independently at a similar answer around the same time. Kruskal built a new coordinate system, now called Kruskal-Sekeres coordinates, specifically designed to describe the region near and inside a black hole's horizon without the artificial infinities that had confused everyone for 40 years. And when Kruskal laid the full geometry out on paper using these new coordinates, something unexpected happened. The diagram that resulted, now known as a Kruskal diagram or a Penrose-Carter diagram in its more refined form, didn't have two regions. It had four, arranged like four quadrants around a central crossing point, each one a genuinely distinct piece of space-time, mathematically connected to its neighbours but physically walled off from at least some of them by horizons that only let information travel one direction. it helps to actually picture the shape of that diagram, because the geometry itself is doing real explanatory work, not just decorating the idea. Draw two lines crossing each other like an X. The region to the right of the X in this picture is the ordinary universe, the part where you're standing right now reading this. The region above the X is the black hole interior. Anything that crosses into that wedge is doomed to reach the singularity at its narrow top, no matter which direction it tries to move, because in that region, moving toward the future and moving toward the center have become the same instruction. The region to the left of the X is the second, causally separate universe, a parallel exterior, mathematically valid, physically unreachable from our side, since nothing that starts in our universe can cross the horizon lines that wall it off. And the region below the X, the mirror image of the black hole wedge, sitting in the diagram's past rather than its future, is the white hole. Notice what the geometry is actually telling you here, because it's more specific than a white hole is a reversed black hole. In this diagram, the white hole region isn't in your future, it's in your past. Anything inside that lower wedge is, according to the geometry, already on its way out, already committed to crossing into either our universe or the parallel one, unable to do anything but move away from the singularity at the wedge's base, the same way anything in the black hole's future wedge is unable to do anything but move toward its singularity. Time, inside that region, only runs outward. There is no version of standing still in a white hole, and there is no version of turning around and going back to look at what's inside it, because inside it is your own past, not a place you can revisit. That's a genuinely different object than a black hole running in reverse, even though the phrase is a useful first approximation. A black hole is a trap, a region you can enter freely but never leave, defined by its future. A white hole is an expulsion, a region you can never enter, defined by its past, that has apparently already ejected everything it was ever going to eject before you arrived to ask about it. One is a door that only opens inward. The other isn't really a door at all. It's closer to the aftermath of a door slamming forever, in a direction nothing can walk against. There's an additional wrinkle worth naming here, because it comes up in almost every serious discussion of this geometry, and it clarifies why physicists spent so long treating the whole four-region picture as more of a mathematical curiosity than a physical prediction. The second exterior, the parallel universe sitting to the diagram's left, is connected to our own universe in this idealized picture by a bridge running through the middle of the diagram, a narrow throat linking the two exterior regions at a single instant. This is the structure now popularly known as an Einstein-Rosen bridge, first described by Einstein himself along with the physicist Nathan Rosen in 1935, and it's the mathematical ancestor of what popular science writing usually calls a wormhole. The catch, and it's a serious one, is that this bridge closes before anything can cross it. Work through the geometry carefully, and the throat connecting the two universes pinches shut faster than light could ever travel through it, collapsing the passage before any traveller, any signal, any single photon could make it from one side to the other. It's a bridge that exists mathematically for a finite and vanishingly brief window, and then is gone, having transported nothing. This is sometimes called the Einstein-Rosen bridge's non-traversability, and it's one of the first hints, decades before anyone worked out the white hole instability directly, that this four-region geometry, however elegant on paper, might be describing something the universe is structurally uninterested in actually letting happen. That idealized, eternal, four-region solution is what's technically called the maximally extended Schwarzschild geometry. Maximally extended meaning it includes every region the mathematics permits, not just the ones relevant to an ordinary collapsing star. And this distinction matters enormously for the rest of this book, because it's the seed of the very question that will occupy every chapter from here forward. A real black hole, the kind astronomers actually observe, doesn't form this way. It forms from a collapsing star. Matter falls inward, crosses a threshold, and a horizon forms around it, with a black hole interior region, but crucially without a fully formed white hole region, without a parallel universe, without an Einstein-Rosen bridge to anywhere. The four-region picture is what you get if you idealize a black hole as having existed forever, eternally, with no formation event, no collapsing star, no beginning at all. A mathematically clean toy model that turns out to be almost nothing like how black holes actually come into being in the observable universe. That gap between the eternal, four-room mathematical ideal and the messier, formation-based reality of every black hole ever actually observed is exactly where the white hole's trouble begins. Because if white holes only exist in the idealized eternal version of the geometry, and nothing in nature ever produces that idealized version from scratch, then the white hole isn't just rare. It's a feature of a toy model that reality was never actually building in the first place, present in the equations the way a perfect frictionless plane is present in a physics classroom, entirely real as mathematics and never once encountered outside of it. But that's getting ahead of the argument. Before asking whether nature ever builds a white hole, a question this book will return to directly with hard observational numbers in Chapter 6. There's a more immediate question worth asking first. Suppose, for the sake of argument, that a white hole geometry did somehow come into being, however that might happen, wherever the matter or the mathematics required to make it might come from. What would it actually look like up close to something approaching it from the safety of the ordinary universe outside? What kind of boundary exactly would it present? That's the next room in the house. Time to open the door, a hole that only lets you out. Picture the boundary itself, not the object, just the edge. A black hole's horizon works one way. Cross it, and there is no equation, no thrust, no trick of engineering that gets you back out. Everything, light, matter, information, a shout, moves inward and only inward once it passes that line. A white hole's horizon is that same rule, flipped. Nothing can cross into it, not light aimed directly at it, not a stray hydrogen atom drifting by for 1 billion years, not the faintest trickle of cosmic background radiation that fills every cubic meter of space and touches everything eventually. The horizon simply will not let anything through in that direction, ever. What it does allow is outward motion. Matter streams out. Light streams out. It behaves from the outside like a fountain that never runs dry and was never seen being filled, pouring outward into space, indifferent to whatever tries to approach it from the far side. Sit with that for a second, because it's easy to let it pass as a neat symmetry and move on. A black hole absorbs. A white hole would only offer, One is a mouth. The other, if it existed, would be something closer to a wound that only ever bleeds outward, never closing, never receiving. It isn't the opposite of a black hole so much as its unreachable reflection, visible in the mathematics, untouchable in the sense that matters most. Nothing that falls toward it ever finds out what's on the other side, because nothing is ever let in far enough to ask. That one-way property sounds elegant on paper. It's also, as the next few chapters will show, the exact reason the whole idea starts to come apart. But before getting to why it comes apart, it's worth understanding the mechanics of the boundary itself a little more precisely, because the phrase one-way membrane undersells how strange the geometry actually is at that edge. A black hole's horizon is defined technically as the boundary of the region from which light cannot escape to infinity, the outermost edge past which even a photon fired directly outward at the maximum possible speed still ends up pulled back toward the centre. It's not that gravity is simply very strong there. It's that the geometry of space itself has been bent to the point where the direction that used to mean outward no longer leads outward at all. Every path forward in time, inside that boundary, leads deeper in. There's no clever angle, no burst of thrust, no configuration of engines that changes this, because it isn't a matter of overcoming a force. It's a matter of there no longer being a way to move toward. A white hole's horizon is the same geometric fact, mirrored. Past a certain distance, no path forward in time leads toward the object. Every trajectory, no matter how it's aimed, no matter how much thrust is applied against it, ends up carried away from the boundary rather than into it. This is the crucial detail that separates a white hole's horizon from something merely repulsive, like the way two like-charged particles push apart. A repulsive force can, in principle, be overcome by enough opposing force. A white hole's horizon isn't offering resistance that a strong enough push could beat. It's redefining at a geometric level which direction counts as the future for anything near it. And the future for anything near a white hole's horizon simply does not include the region inside it. There's no strength of engine that fixes that, any more than there's a strength of engine that lets you travel to yesterday. This is worth dwelling on because it clears up a common intuition trap. People hearing about white holes for the first time often picture something like a cosmic wall or a very powerful outward wind, an obstacle you could, with enough force, push against and possibly punch through. That picture is wrong in a specific and important way. It's not an obstacle in the sense of a wall or a wind. It's closer to a one-way sign carved directly into the structure of causality itself at that location. The horizon isn't preventing entry the way a locked door prevents entry. It's preventing entry the way, before you were born, prevents you from attending your own birth. It's not a barrier you failed to overcome. It's a direction that doesn't exist for you to travel in. Think about what this does to the experience of an observer trying to approach one, hypothetically, in a very fast, very well-shielded spacecraft. As you approach a black hole's horizon, the geometry gradually squeezes your options, but right up until the moment you cross, you still have some freedom. You can fire your engines and pull away, hover in place with tremendous thrust, adjust your trajectory. It's only at the horizon itself that your options collapse entirely, all future paths bending inward at once. A hole that only lets you out, Picture the boundary itself, not the object, just the edge. A black hole's horizon works one way. Cross it, and there is no equation, no thrust, no trick of engineering that gets you back out. Everything, light, matter, information, a shout, moves inward and only inward once it passes that line. A white hole's horizon is that same rule, flipped. Nothing can cross into it, not light aimed directly at it, not a stray hydrogen atom drifting by for 1 billion years, not the faintest trickle of cosmic background radiation that fills every cubic meter of space and touches everything eventually. The horizon simply will not let anything through in that direction, ever. What it does allow is outward motion. Matter streams out. Light streams out. It behaves from the outside like a fountain that never runs dry and was never seen being filled, pouring outward into space, indifferent to whatever tries to approach it from the far side. Sit with that for a second, because it's easy to let it pass as a neat symmetry and move on. A black hole absorbs. A white hole would only offer. One is a mouth. The other, if it existed, would be something closer to a wound that only ever bleeds outward, never closing, never receiving. It isn't the opposite of a black hole so much as its unreachable reflection, visible in the mathematics, untouchable in the sense that matters most. Nothing that falls toward it ever finds out what's on the other side, because nothing is ever let in far enough to ask. That one-way property sounds elegant on paper. It's also, as the next few chapters will show, the exact reason the whole idea starts to come apart. But before getting to why it comes apart, it's worth understanding the mechanics of the boundary itself a little more precisely, because the phrase one-way membrane undersells how strange the geometry actually is at that edge. A black hole's horizon is defined technically as the boundary of the region from which light cannot escape to infinity, the outermost edge past which even a photon fired directly outward at the maximum possible speed still ends up pulled back toward the centre. It's not that gravity is simply very strong there. It's that the geometry of space itself has been bent to the point where the direction that used to mean outward no longer leads outward at all. Every path forward in time, inside that boundary, leads deeper in. There's no clever angle, no burst of thrust, no configuration of engines that changes this, because it isn't a matter of overcoming a force. It's a matter of there no longer being a way to move toward. A white hole's horizon is the same geometric fact, mirrored. Past a certain distance, no path forward in time leads toward the object. Every trajectory, no matter how it's aimed, no matter how much thrust is applied against it, ends up carried away from the boundary rather than into it. This is the crucial detail that separates a white hole's horizon from something merely repulsive, like the way two like-charged particles push apart. A repulsive force can, in principle, be overcome by enough opposing force. A white hole's horizon isn't offering resistance that a strong enough push could beat. It's redefining at a geometric level which direction counts as the future for anything near it. And the future for anything near a white hole's horizon simply does not include the region inside it. There's no strength of engine that fixes that, any more than there's a strength of engine that lets you travel to yesterday. This is worth dwelling on because it clears up a common intuition trap. People hearing about white holes for the first time often picture something like a cosmic wall or a very powerful outward wind, an obstacle you could, with enough force, push against and possibly punch through. That picture is wrong in a specific and important way. It's not an obstacle in the sense of a wall or a wind. It's closer to a one-way sign carved directly into the structure of causality itself at that location. The horizon isn't preventing entry the way a locked door prevents entry. It's preventing entry the way, before you were born, prevents you from attending your own birth. It's not a barrier you failed to overcome. It's a direction that doesn't exist for you to travel in. Think about what this does to the experience of an observer trying to approach one, hypothetically, in a very fast, very well-shielded spacecraft. As you approach a black hole's horizon, the geometry gradually squeezes your options, but right up until the moment you cross, you still have some freedom. You can fire your engines and pull away, hover in place with tremendous thrust, adjust your trajectory. It's only at the horizon itself that your options collapse entirely, all future paths bending inward at once. A white hole works the same way, but the collapse of options happens as you approach from outside, not as you cross a threshold. Get close enough, and the geometry itself begins steering you away regardless of what your engines are doing, more and more insistently, until at the horizon the steering becomes absolute, every trajectory without exception bent outward, away, back into the ordinary universe you started in. There's a subtler consequence buried in this that's easy to miss on a first pass, and it's one that later chapters lean on directly. Because nothing can cross a white hole's horizon, a white hole can never gain mass. A black hole, by contrast, grows constantly and unremarkably. Every particle of gas it swallows, every star it tidally shreds and consumes, every photon that wanders too close, adds incrementally to its mass, and astronomers watch this happen routinely, mapping the slow, steady growth of black holes at the centers of galaxies over cosmic time, through the X-ray glow of infalling material heating up as it spirals inward. A white hole has no equivalent process available to it, structurally by definition. It cannot accrete. It cannot merge by absorption, the way two black holes merge by colliding and combining. Whatever mass a white hole is ever going to have, it has from the very first instant of its theoretical existence, unchangeably, because the one thing that would let it change, letting something in, is precisely the one thing its geometry forbids. That single structural fact quietly answers a question that might otherwise seem unrelated. Why don't astronomers expect white holes to grow into supermassive versions the way black holes do, anchoring galaxies, warping the orbits of entire star systems around them? It's not merely that nobody has observed a supermassive white hole. 3 billion years of nothing very interesting biologically speaking, before anything with the nervous system showed up. The body that you have right now, the one that is horizontal somewhere, the one that is tired, is the product of 600 million years of increasingly complicated multicellular experiments built on 3 billion years of microbial chemistry, built on a carbon cycle that worked because the water stayed. The water stayed because the distance was right and the field held and the tectonics ran and the sun was dim enough, early enough for long enough. None of that was for you. There was no for. It just went the way it went. And this is what the going produced. Something aware enough to be curious about the planet that did not go this way. Something tired enough at this hour to be lying still on a surface that has been pulling things toward its center for 4.5 billion years, above a carbon cycle that is still running on a planet that kept its water. That is not heroic. That is not a story of survival or fitness or design. That is one trajectory among the possibilities, the one that happened to include you, and that included the Sleepy Science Channel, which is still here partly because people keep choosing to be part of it, and that is the closest thing to luck having a witness. One photon is enough to end it. By the early 1970s, a few physicists had stopped admiring the white hole solution and started stress testing it. The question was simple enough to ask out loud in a seminar room. What happens if something, anything, tries to interact with a white hole from outside? Not a star, not a shockwave, a single photon. The physicist Douglas Erdely worked through what happens to even the faintest trickle of radiation approaching a white hole's horizon, the kind of low-level background light that exists everywhere in the universe, all the time, whether anyone is watching for it or not. And the horizon does something to that photon that a black hole's horizon does not do in the same way. It doesn't reflect it. It doesn't absorb it, since nothing can be absorbed. It stretches time around it until the photon's energy, from the white hole's own reference frame, becomes effectively infinite. That's not a metaphor for very large. It's closer to a mathematical wall, blue shift without a ceiling. And once you put infinite energy at a boundary that the whole geometry depends on being calm and empty, the geometry cannot hold its shape. The white hole solution, the moment anything at all approaches it, stops being able to describe what happens next. Physicists call this a horizon instability, and the striking part isn't that it happens under extreme conditions. It happens under the mildest conditions imaginable. The ordinary hum of radiation that fills every region of space, the kind of noise no vacuum has ever managed to be quiet enough to avoid. A black hole can shrug off a wandering photon without any trouble. A white hole, according to the same equations that produced it in the first place, cannot survive being looked at more or less. The very thing required to notice it appears to be the thing that ends it. To see why this happens, and why it happens so easily, it helps to walk through the mechanism directly rather than take the conclusion on faith. Picture a single photon, left over from some ancient stellar explosion, drifting through space with an entirely unremarkable amount of energy. The kind of photon that passes through a given patch of sky uneventfully, billions of times a second, everywhere in the universe without incident. Aim it, hypothetically, toward a white hole's horizon. As that photon approaches the boundary, it encounters the mirror image of the effect described back in Chapter 1, the redshift that stretches light falling toward a black hole. Except here, the direction is reversed, and so is the sign of the effect. Instead of being stretched toward longer, weaker wavelengths as it falls, the photon is compressed toward shorter, more energetic ones as it approaches. This is ordinary blue shift, the same phenomenon that makes an ambulance siren rise in pitch as it races toward you, except where the siren effect is gentle and bounded by the speeds involved. The blue shift near a white hole's horizon is governed by the same runaway time dilation mathematics that made the black hole's redshift stretch toward infinity in the first place, just flipped in direction. Here's the part that makes this genuinely different from an ordinary blue shift, the kind that happens harmlessly every time you drive toward a light source. In an ordinary blue shift, the effect is capped by how fast the source and observer are actually moving relative to each other. Faster relative motion, more blue shift, but always some finite, calculable amount. Near a white hole's horizon, the effect isn't capped by relative velocity in any ordinary sense. It's governed by the geometry of the horizon itself, the same geometry that makes clocks near a black hole's boundary appear, to a distant observer, to slow toward a full stop without ever quite reaching one. Run that same time dilation mathematics in reverse, as a white hole's geometry requires, and instead of a clock slowing toward a stop, you get a photon's energy climbing toward a ceiling that the mathematics never actually supplies. There isn't a maximum. The blue shift simply keeps compounding geometrically the closer the photon's calculated approach gets to the horizon, all the way to a mathematical infinity. That's the finding Erdely published, along with several collaborators working through the same problem from slightly different angles around the same period. Physicists including Robert Wald and, in later work synthesizing and extending the result, Valery Frolov and Igor Novikov, whose textbook on black hole physics remains one of the standard references on exactly this instability. The specific technical term for what they found is that the white hole horizon is subject to what's called an infinite blue shift, or sometimes a curvature singularity forming dynamically at the horizon itself, distinct from and arriving much sooner than the pre-existing singularity that was already supposed to sit at the white hole's core. It's worth being precise about what infinite is doing in that sentence, because it's not being used loosely, the way people sometimes say a headache is killing them. In physics, when a calculation returns an infinite value for something that's supposed to be physically meaningful, energy, curvature, density, that infinity is usually a signal that the theory being used has been pushed past the domain where it's trustworthy. It isn't that nature is literally handing back an infinite number of joules to some passing photon. It's that general relativity, asked to describe what happens to a white hole's horizon under even the gentlest possible external influence, responds by breaking down entirely, refusing to produce any finite sensible answer for what should happen next. The theory isn't predicting an extreme event, it's declining to predict anything at all, because the scenario it's being asked to describe no longer resembles anything the theory can meaningfully model. This matters because it changes the shape of the claim being made in this chapter. The claim isn't a white hole would experience a very violent, very energetic disruption if disturbed. The claim is stronger and stranger the moment any external influence, however faint, reaches a white hole's horizon. The mathematics that was supposed to describe the object simply stops functioning. Not damaged, not overwhelmed, undefined. The horizon, under the lightest possible touch, transitions from a boundary general relativity can describe to a boundary general relativity has nothing left to say about, and that transition, according to every calculation done on it since the 1970s, happens essentially instantly on any time scale a clock could register. There's a useful comparison here to a very different, much more familiar kind of instability, because it clarifies just how sensitive this failure mode actually is. Consider a pencil balanced perfectly on its point. In principle, in an idealized, frictionless, perfectly symmetric world, that pencil could balance there forever, at genuine equilibrium, obeying every law of physics without contradiction. In practice, it never does, because the equilibrium is unstable. The tiniest disturbance, an air current too faint to feel, a vibration too small to measure, is enough to send the pencil toppling, and once it starts falling, nothing brings it back to balance. Physicists describe this by saying the balanced state is real, but not stable, mathematically permitted, but so sensitive to perturbation that no realistic environment ever preserves it for more than an instant. The eternal, undisturbed white hole solution is something like that balanced pencil, except more extreme in a specific way. A pencil topples because of an external push. The pencil itself remains a perfectly ordinary object throughout. It just changes orientation. A white hole's horizon under an equivalent disturbance doesn't merely tip over into some new but still describable configuration. It runs into a mathematical wall that the theory has no vocabulary for crossing. There's no fallen over white hole waiting on the other side of the disturbance the way there's a pencil lying flat on the table waiting on the other side of the fall. There's just the edge of what general relativity can say, arrived at almost instantly, with nothing charted beyond it. It's also worth noting what this instability does and doesn't depend on, because it rules out an obvious escape hatch. You might reasonably ask whether this problem only applies to some idealized, perfectly isolated white hole, and whether a more realistic version, sitting in a less pristine environment, perhaps shielded somehow, perhaps interacting with matter in some more gradual, less catastrophic way, might sidestep the issue. The calculations don't support that hope. The instability isn't a special case result that only shows up under contrived worst-case conditions. It shows up for the ordinary cosmic microwave background alone, the faint, nearly uniform radiation left over from the early universe, present at a temperature of roughly 2.7 degrees above absolute zero in literally every direction, everywhere, with no location in the observable universe cold enough or empty enough to be entirely free of it. If a white hole's horizon can't survive contact with the CMB, it can't survive contact with anything, because there is nowhere in the actual universe quiet enough to spare it that contact. This is the detail that turns the instability from an interesting mathematical footnote into something closer to a law of exclusion. It isn't saying white holes are fragile and might be destroyed by sufficiently violent events. It's saying white holes cannot coexist even briefly with the background hum that fills every corner of space-time, and that hum isn't optional, isn't avoidable, isn't a condition some lucky white hole might happen to escape by forming in an unusually empty pocket of the cosmos. There is no unusually empty pocket. The cosmic microwave background reaches everywhere, discovered by accident in 1965 by two radio astronomers who initially thought the persistent noise in their antenna was pigeon droppings, and confirmed since as one of the most uniform, most thoroughly mapped phenomena in all of observational cosmology. So the picture that emerges from this chapter is narrower and more absolute than white holes are unstable. It's this: the version of a white hole that appeared in the clean, idealized mathematics, eternal, undisturbed, sitting in perfect isolation, requires a condition, total isolation from all external radiation, that the actual universe has never once provided anywhere, at any time, to anything. The instant that condition is violated, which is to say the instant the white hole exists in anything resembling the real universe rather than a sealed mathematical vacuum, the horizon runs into an infinity it cannot resolve, and the theory describing it goes silent. What happens physically, in whatever sense physically still applies once the describing theory has broken down, is the subject of the next chapter, because the story doesn't end with an undefined mathematical result. Something has to happen next, even if general relativity itself can no longer say precisely what. And working through what a full-scale collision between an eternal universe's worth of incoming radiation and a boundary that can't accept it gradually actually looks like turns out to be even stranger than the instability itself. Everything that ever fell toward it arrives at once. Widen out first. Across the history of the universe, an enormous amount of radiation has been drifting outward in every direction. Light from ancient stars, background radiation left over from an early hot universe, gravitational waves from collisions no one recorded at the time. All of it, everywhere, all the time, moving. Now imagine a white hole sitting somewhere in that field for its entire theoretical existence, patiently not letting any of it in. Except the mathematics doesn't allow patiently, because nothing can cross the horizon gradually, trickling in over years the way dust settles on a black hole slowly over cosmic time. Everything that was ever going to approach that boundary arrives compressed into a single instant. Not a long moment, not even a short one. A moment with no duration a clock could register. Zoom in now, all the way down, to the horizon itself in that instant. Every photon that any observer, anywhere, would ever have sent toward this object, across the entire remaining lifetime of the universe, shows up stacked on top of itself, all at once, right there. It's not a flood arriving quickly. It's a flood arriving without a when. The energy involved isn't just large in the ordinary sense that a supernova is large. It's the kind of concentration that general relativity itself refuses to hand back a sensible answer for. The equations produce something closer to a fresh singularity, a new one, forming exactly at the boundary meant to keep everything out. So the white hole doesn't get worn down over billions of years the way a black hole slowly gains mass from its surroundings. It ends, structurally, in the very first instant it would have needed to survive contact with the rest of the universe. The instant every future is quietly compressed into. It's less a boundary that failed under pressure, and more a boundary that never had a version of later available to it in the first place. To understand why the arriving radiation compresses this way, instead of simply piling up gradually, it helps to go back to the geometry laid out in Chapter 2 and follow one specific consequence of it all the way through. Recall that in the maximally extended Schwarzschild picture, the white hole region sits in a diagram's past wedge. Everything inside it is already, structurally, on its way outward, and the region itself has a kind of one-shot character to it, existing for a single finite interval in the overall geometry rather than persisting indefinitely the way the exterior universe does. The horizon that faces outward from that wedge isn't a surface sitting there for all time, patiently declining entry to whatever approaches it on any given day. It's a surface that exists for exactly as long as the white hole geometry itself exists, and coordinated with it precisely. Here's the consequence that matters, because the horizon has, in effect, a beginning and a rapidly closing window. any radiation that would ever have reached it, from any point in the future history of the universe outside, has to be accounted for within that same narrow window, mathematically, rather than spread out across the actual cosmic timescales over which it was really emitted. A photon that, from a normal observer's perspective, wouldn't reach the vicinity of the object for another 10 billion years still, in the horizon's own accounting, has to be folded into the geometry's finite lifespan. The mathematics doesn't have the option of saying we'll deal with that photon later, because for the white hole horizon, in this classical eternal solution, there effectively is no later. There's only the single window in which the whole one-way structure is defined at all. This is a genuinely different mechanism from the horizon instability described in Chapter 4, even though the two are closely related and often discussed together, and it's worth being precise about the distinction. The early instability from the previous chapter shows that a single infalling photon, blue-shifted without limit, is already enough to break the geometry. That's a statement about the horizon's sensitivity to even the faintest possible disturbance. This chapter's argument, sometimes discussed under the heading of mass inflation, closely related to work done later by Eric Poisson and Werner Israel on the interior structure of realistic black holes, makes a related but distinct point. It's not just that any single disturbance is enough. It's that the geometry's own structure forces every disturbance that would ever occur across the object's entire theoretical existence to converge on the horizon at effectively the same instant, compounding an already fatal sensitivity into something closer to an inevitability rather than a mere vulnerability. It's worth pausing on the phrase compressed into a single instant, because it can sound like poetic exaggeration rather than a literal mathematical result, and it isn't exaggeration at all. It falls directly out of doing the calculation in the right coordinates. Recall from Chapter 1 that time dilation near a horizon isn't a minor correction. It's a runaway effect, stretching or compressing intervals without any natural ceiling as you approach the boundary itself. Apply that same runaway compression to the entire future history of radiation that would, from a distant observer's perspective, spend billions of years slowly making its way toward the object, and from the horizon's own local perspective, that entire multi-billion-year drip becomes indistinguishable from a single simultaneous arrival. It's the same mathematics that made a falling object's descent look, from outside, like it never quite finishes, just run through the opposite geometry, with the opposite consequence. Instead of an infinite stretching out of arrival, you get an infinite compression of it. There's a way to make this concrete with an image, even though the underlying mathematics is considerably more abstract than any single image can fully capture. Picture every letter ever going to be mailed to a single address, across the entire remaining history of a postal system that will run for billions of years, arriving in one envelope on one specific morning, all at once, indistinguishable from each other by the time they land on the doormat. The postal worker delivering that envelope isn't handling an unusually heavy load. They're handling something that has stopped behaving like mail at all, an object that has in effect swallowed an entire future's worth of a process and rendered it into a single event with no internal structure left to examine. This is, in a very real sense, what the horizon of a white hole is being asked to absorb, structurally, the instant it's placed in contact with an ordinary universe full of ordinary background radiation, rather than the artificially sealed vacuum the idealized solution assumes. And the object built to receive that compressed, infinite arrival isn't built to receive it at all. It's built by definition to receive nothing, ever, from any direction. The horizon that cannot let anything cross inward is being handed, in this scenario, the entire compressed future of everything that would ever have approached it, and it has no mechanism whatsoever for processing that arrival gracefully, because receiving something gracefully was never part of its design in the first place. What the calculation actually produces, worked through by physicists studying this exact question in the years following Erdely's original result, is the formation of a new curvature singularity, not the original one sitting at the mathematical centre of the white hole geometry inherited from its past, but a fresh one, forming dynamically right at the horizon itself, essentially the instant the object is exposed to any external environment at all. This is sometimes described as the horizon closing up into a singularity, or as the white hole horizon undergoing gravitational collapse of its own, in a strange echo of the very process, stellar collapse into a black hole, that the white hole was supposed to be the mirror image of in the first place. There's an irony worth naming directly here, because it closes a loop that opened all the way back in Chapter 1. A black hole forms because matter collapses inward under its own gravity, crushing itself past the point of no return into a singularity. A white hole, according to this chapter's argument, effectively forms a singularity of its own kind through exactly the same basic mechanism, an overwhelming concentration of infalling energy crushing space-time past the point where the equations can describe it, except that in the white hole's case, the infalling energy isn't matter that chose to fall in. It's the mathematically unavoidable, infinitely compressed echo of everything the universe was ever going to send toward it, arriving all together because the geometry gives it no other option. Put differently, a black hole and a white hole on the surface look like structural opposites. One only takes, one only gives. But trace what actually happens the instant either one is placed in contact with a realistic universe, and they converge on something eerily similar. The black hole collapses inward because of what it accumulates. The white hole, unable to accumulate anything gradually, still ends up collapsing under the weight of everything it would ever have accumulated, delivered all at once, with none of the billions of years of buffer that made the black hole's version of this process survivable and ordinary rather than instantly catastrophic. This is the point at which the phrase, "white holes can't survive their own physics," the title framing this entire book, stops being a rhetorical flourish and starts being closer to a literal, calculable statement. It isn't that white holes are destroyed by some external threat they failed to anticipate or defend against. It's that the geometry which defines a white hole in the first place, the same geometry responsible for its one-way horizon, its outward-only causal structure, its origin in a past singularity rather than a future one, is also, unavoidably, the geometry that guarantees its own destruction the instant it's placed in anything resembling the actual universe. The instability isn't bolted onto the white hole from outside. It's built into the object's own foundation, present in the same mathematics that makes the object what it is. None of this, notably, addresses the separate question of whether a white hole would ever actually come to exist in the first place, whether nature has any process, anywhere, capable of producing one even briefly, even doomed to near-instant collapse. That's a different kind of question, an observational one rather than a theoretical one, and it turns out to have an answer just as stark as everything in this chapter, though arrived at by an entirely different method. Not equations on a chalkboard, but decades of telescopes pointed at the sky, watching patiently for something that has never once shown up. Nothing in nature has ever made one of these. Somewhere in almost every galaxy right now, a star massive enough is finishing its life. Fuel runs low, the core stops holding its own weight against itself. It collapses, sometimes into a neutron star, sometimes, if it's massive enough, into a black hole. This has happened, by conservative estimates, hundreds of millions of times across the observable universe. It's not rare, it's routine, in the way that autumn is routine. Now ask the mirror question. How many times has a white hole formed the same way? From a collapsing star, a merger, an explosion, any known astrophysical process at all? 0. Not rare. 0. Every survey ever run, every gamma-ray burst catalogue, every gravitational wave detection from the LIGO and Virgo observatories has turned up plenty of evidence for black holes forming and merging. Not one has ever produced a signature consistent with a white hole coming into being. Not a candidate, not a disputed case debated at conferences. Nothing. That absence used to be treated as a gap in observation, the kind of thing better instruments might eventually fill in. It's been decades since that excuse held up. The instruments have improved by orders of magnitude. The silence hasn't changed. At some point, an absence stops looking like a coincidence and starts looking like a rule the universe is quietly enforcing. Nature builds black holes constantly, almost carelessly, out of ordinary stellar death. It has never once, as far as anyone has been able to tell, built the other one. It's worth being specific about exactly how thorough this search has actually been, because nobody has found one can sound like a modest claim, when in fact the observational net cast for this particular object has been unusually wide, unusually long-running, and unusually well-suited to catching exactly the kind of signature a white hole would be expected to produce if the idea has any physical merit at all. Start with gamma-ray bursts, because they occupy a genuinely interesting place in this story. Not as evidence for white holes, but as the closest thing the field has ever had to a serious testable proposal connecting the two. Gamma-ray bursts are among the most energetic events ever observed in the universe. Brief flashes of high-energy radiation, some lasting only a fraction of a second, others lasting several minutes, bright enough to be detected across billions of light-years. Most are now well understood as the products of either the collapse of extremely massive, rapidly rotating stars into black holes, or the violent merger of two neutron stars. Both processes that produce black holes, or neutron stars, not white holes, and both confirmed through follow-up observations that identified the host galaxies, the associated supernovae, and in the case of neutron star mergers, matching gravitational wave signals detected by LIGO and Virgo in coincidence with the gamma-ray flash itself. But in the 1990s, before that consensus fully solidified, a handful of physicists, including, In one notable proposal, Stephen Hawking's collaborator Igor Novikov, and separately the Italian physicist Remo Ruffini working with colleagues, floated the idea that at least some subset of gamma-ray bursts might instead be evidence of white holes forming, or of primordial black holes transitioning into white hole-like bursts through the kind of quantum bounce mechanism that Chapter 9 of this book will examine directly. The proposal had a certain appeal at the time. Gamma-ray bursts were, for years, genuinely mysterious, their origin unclear, their energetics difficult to explain with known astrophysical processes, and a sudden, violent release of matter and radiation from a compact source was at least superficially reminiscent of what a white hole's brief, catastrophic contact with the outside universe, as described in chapters 4 and 5, might be expected to produce. That proposal did not survive contact with better data. As gamma-ray burst astronomy matured through the late 1990s and 2000s, helped enormously by satellites like BeppoSAX, SWIFT, and Fermi, which could localize bursts precisely enough for ground-based telescopes to identify their host galaxies and afterglows. The observed properties of gamma-ray bursts turned out to match the collapsar and neutron star merger models with increasing and eventually overwhelming precision. The energy budgets, the durations, the correlation with star-forming regions for long bursts, and with older stellar populations for short bursts, the afterglow spectra, the eventual direct detection of gravitational waves from a neutron star merger in 2017, arriving within under 2 seconds of a corresponding gamma-ray burst. All of it built toward a picture with no need for and no room left over for a white hole explanation. The white hole gamma-ray burst hypothesis wasn't dramatically disproven in a single decisive experiment. It was quietly outcompeted, explanation by explanation, burst by burst, until nothing was left that required it. Gravitational wave astronomy tells an even more direct version of the same story, and it's worth understanding why gravitational waves are such a well-suited tool for this particular search. When two black holes spiral into each other and merge, the resulting gravitational wave signal has an extremely distinctive shape. A rising chirp as the two objects orbit faster and faster, peaking sharply at the moment of merger, and then a specific pattern of decay called a ring down as the newly merged black hole settles into a stable, rotating final state. That ring down pattern is itself a signature of the object's horizon. It's essentially the horizon's own natural vibration, damping out, and it carries information about the mass and spin of whatever formed. Physicists have proposed in a modest number of theoretical papers over the past decade that if compact objects other than ordinary black holes exist, including, hypothetically, horizonless alternatives or white hole-like remnants, their ring-down signatures might differ in specific calculable ways from the standard prediction, potentially showing echoes, repeated smaller signals arriving after the main ring down, caused by radiation reflecting off some structure at or near where a horizon would ordinarily be. Several dedicated searches for exactly these echoes have been carried out on real LIGO and Virgo data, going back and specifically re-examining the loudest, cleanest merger events for any sign of this predicted repeating pattern. The results, across every search conducted so far, have been consistently negative. No statistically significant echo signal has been found in any of the events analysed, and the merger ringdowns observed to date remain fully consistent with ordinary black holes possessing ordinary one-way horizons, with no evidence of anything unusual happening at or near the boundary that a white hole-like alternative might have predicted. This doesn't close the door on every conceivable exotic alternative to a standard black hole horizon. Physicists are careful, in these papers, to note the limits of what current instrument sensitivity can rule out. But it adds another independent, high-precision line of evidence, pointing the same direction as everything else in this chapter. Wherever astronomers have looked, using whatever method available, the signature expected of a white hole has simply never turned up. There's a broader point buried in this pattern that's worth drawing out explicitly, because it changes how the absence should be read. It would be one thing if the search for white holes had been narrow, confined to a single wavelength of light, or a single type of instrument, or a short window of observing time. It hasn't been. The search has spanned gamma rays, X-rays, optical light, radio waves, and now gravitational waves, across observing campaigns running from the 1960s to the present day, using instruments that have improved in sensitivity by many orders of magnitude over that span. Each new generation of instruments has, if anything, made a genuine white hole signature easier to catch, not harder. More sensitive detectors, better localization, longer baselines, more sky coverage, more archived data to search back through. And across every one of those improvements, across every one of those independent channels, the answer has stayed the same. Not difficult to detect, not at the edge of current sensitivity, simply absent. Compare this one more time to the black hole side of the ledger, because the contrast is what makes the absence so striking rather than merely unsurprising. Black holes have been confirmed through direct imaging. The Event Horizon Telescope's pictures of the shadows cast by the supermassive black holes at the centres of the galaxy M87 and our own Milky Way, released in 2019 and 2022 respectively. They've been confirmed through stellar orbits, decades of precisely tracked stars whipping around an invisible, immensely massive object at the centre of our galaxy, work that earned Reinhard Genzel and Andrea Ghez a share of the 2020 Nobel Prize in Physics. They've been confirmed through X-ray binaries, through tidal disruption events where a star is visibly shredded by an unseen companion, and since 2015, through dozens of confirmed gravitational wave detections of black holes merging with other black holes, catalogued in increasingly large numbers as detector sensitivity has improved. Black holes are, at this point, one of the most thoroughly independently confirmed categories of object in all of astrophysics. White holes have none of this, not a partial version of this, not a single tentative candidate awaiting confirmation, the way genuinely uncertain astrophysical claims usually look while they're being worked out, a handful of ambiguous data points, competing interpretations, a slow convergence toward consensus one way or the other over several years of follow-up study. White holes have simply never generated a candidate worth debating in the first place. The observational record isn't inconclusive on this question. It's uniform, and it's been uniform for as long as anyone has been looking. This chapter's argument, then, isn't that white holes are hard to find. Plenty of real astrophysical phenomena were hard to find for decades before better instruments finally caught them. Gravitational waves themselves went undetected for a full century after Einstein predicted them, until the technology to catch them finally caught up. The argument here is different, and it connects directly back to the theoretical case built across chapters 4 and 5. It isn't merely that nature hasn't happened to build a white hole yet. It's that every known astrophysical process capable of producing a comparably compact, comparably massive object, stellar collapse, neutron star mergers, black hole mergers, produces a black hole every single time it's been observed to run to completion, with never once a white hole appearing as an alternative outcome. Combine that with the instability described in the previous 2 chapters, and the absence stops looking like bad luck. It starts looking like exactly what the theory itself predicts. Not that white holes are simply rare among nature's outcomes, but that nature's known processes were never actually capable of producing the specific, delicate, past singularity-anchored geometry a genuine white hole would require in the first place. Which raises the obvious next question, the one this book has been circling since chapter 2. If ordinary astrophysical collapse can't build one, if there's no observed process anywhere that produces this 4th region of the Schwarzschild geometry, the way stellar collapse reliably produces the black hole region, then what precisely would a white hole's formation even require? What conditions would have to be true, going back through its entire history, for the object to exist at all before the instability described in chapters 4 and 5 even gets a chance to destroy it? That question turns out to have an answer, and the answer is even more demanding than nature hasn't happened to do this yet. It's closer to nature having never been in a position to do this at all. It would need a past that never happened. Start small. A white hole mathematically doesn't form. It simply already exists going back, in its own timeline, to a past singularity, a beginning point baked into the geometry from the start, rather than a collapse that happens partway through. Widen the frame. For that geometry to stay clean and behave the way the equations describe, the region around it would need to have been essentially empty for its entire history. No stray dust drifting through at any point. No ambient light left over from anything. No gravitational ripple passing by. Ever, from the beginning of time up to now. Widen it again. Real space is never that empty. Even the coldest, most isolated pocket of intergalactic void is still bathed in the cosmic microwave background. The faint afterglow of the early universe, present in every direction, unavoidable, discovered by accident in 1965 and never once found missing from any patch of sky since. So a white hole's requirement isn't just difficult. It's not like solving a hard equation. It's closer to asking for a room that has never had a single sound enter it, anywhere, ever, on a planet that has not had a truly silent room since before there was air to carry sound at all. The condition isn't rare. It's the kind of condition the actual universe has never once satisfied in 13.8 billion years of trying. It's worth slowing down on exactly why empty has to mean all the way back, because that's the detail that turns this from an inconvenience into something closer to a structural impossibility. A black hole doesn't have this problem. A black hole can form out of a genuinely messy history. A star that accreted gas unevenly, merged with a companion, got nudged by a passing cluster, absorbed a comet field, whatever actually happened to it over millions of years, because none of that messiness has to be undone for the black hole to exist afterward. The collapse simply proceeds from whatever state the star was actually in. Its horizon forms at the end of the story, and it doesn't care what the earlier chapters looked like. It inherits the past. It doesn't require a particular one. A white hole's horizon runs the opposite way, because nothing can ever cross into it. That was the entire content of Chapter 3. Every bit of that same ordinary messiness stays outside forever, unable to be absorbed, unable to be smoothed over, unable to be folded into the object the way a black hole folds in falling matter into itself. Whatever radiation, dust, or gravitational disturbance the white hole ever encounters has to have simply never arrived, not been deflected, not been absorbed and forgotten, never arrived at any point across its entire causal past, all the way back to whatever moment the beginning means for an object whose past is structurally a singularity rather than a formation event. There's no equivalent of digesting a messy history, because a white hole is defined by refusing digestion altogether. That's where the cosmic microwave background stops being a minor technical objection and becomes something closer to a proof. It isn't a stray inconvenience that happens to be floating around in most of the universe, the kind of thing you could imagine a sufficiently isolated pocket of space, avoiding through sheer distance from any galaxy. It's a local one, a solitary pocket of extreme order sitting in the middle of an otherwise ordinary high-entropy, already evolved universe billions of years into its own history, needing to have arisen, or simply been present, without ever having been produced by anything, and without any of the surrounding disorder ever having touched it. It's not asking for the kind of order the universe started with. It's asking for a second, independent, unexplained instance of that same order, isolated and pristine, sitting inside a cosmos that has spent 13.8 billion years thoroughly mixing itself. There's no known process that manufactures pockets of order like that after the fact. Entropy, once it starts climbing, doesn't hand out local exemptions. Put the two problems together. No ordinary matter or radiation has ever reached it, and no known process has ever produced a fresh, isolated low-entropy region this long after the universe's own low-entropy beginning. And the picture that emerges isn't of an object that's simply rare, the way a specific kind of stellar remnant might be rare. It's of an object whose required history contradicts the two best understood facts about how the universe actually behaves. That it's uniformly filled with leftover light from its own birth, and that order, once lost, doesn't reappear locally without a cause. A white hole doesn't just need to have gotten lucky. It needs a past the universe was never in a position to hand it. There's a tempting escape hatch here, and it's worth closing off explicitly, because a careful reader of Chapter 2 will already be reaching for it. That chapter described a second exterior region buried in the Schwarzschild geometry, a separate, causally disconnected universe that the mathematics permits, but that our universe can never reach. Couldn't a white hole simply belong to that region instead of this one, quietly satisfying its impossible emptiness requirement somewhere we're not obligated to check? It's a fair question, and general relativity doesn't forbid asking it. But it doesn't actually rescue the object, it just relocates the problem. Whatever region a white hole occupies, the same requirement applies within it. Nothing can ever have crossed its horizon from any direction at any point in that region's own history. If that other universe contains anything at all resembling the one we can observe, matter, radiation, structure, the ordinary furniture of a physical cosmos, it faces the identical impossibility, just moved one universe over, still unobservable to us either way, still no closer to being a place a white hole could actually persist. And if it doesn't contain any of that, if it has to be stipulated as perfectly empty by definition just to make the geometry work, then the solution isn't describing a white hole surviving in a real universe. It's describing a white hole surviving in a universe custom built, by assumption, to contain nothing capable of ending it. That isn't a loophole. It's the same argument wearing a different address. It helps to put a number on just how thoroughly the cosmic microwave background rules out the quieter version of this problem, the one that doesn't require reasoning about other universes at all. The background radiation isn't just present, it's almost perfectly uniform, varying in temperature across the sky by only about 1 part in 100,000, and it carries roughly 400 photons in every cubic centimetre of space, everywhere, at a temperature of 2.7 Kelvin, a few degrees above absolute zero. There is no direction you could point a hypothetical white hole's horizon, and no volume of space you could tuck it into where that photon bar thins out to zero. Interstellar space, intergalactic voids, the emptiest regions between superclusters that astronomers have ever mapped. All of it is still awash in this same faint ancient light, arriving from every direction at once, all the time, at a rate no shielding and no distance has ever been shown to reduce to nothing. A white hole doesn't need to avoid a crowded neighbourhood. It needs to avoid the one form of contact that has never, anywhere, been successfully avoided. That's the setup for the next problem, and it follows almost immediately from this one. Even granting, for the sake of argument, that some corner of space-time somehow satisfied this impossible emptiness requirement, and a white hole came into being with a clean, undisturbed past, there's still the matter of where all that outward streaming energy is supposed to have come from in the first place. A past this empty leaves no room for a reservoir, and an object that pours matter and light outward, without ever having taken any in, has a ledger problem of its own, emitting without ever having swallowed anything first. Everything that puts something out in nature has first taken something in. A star radiates light because it is fusing fuel it accumulated over millions of years. A river carries water because rain and snowmelt fed it somewhere upstream. Even a battery only releases energy it was first charged with. Output, everywhere you look, has a matching input somewhere earlier in the story. A white hole breaks that ordering cleanly on paper. It streams matter and radiation outward, in principle without limit, and nothing, no accumulation phase, no charging period, no equivalent of a reservoir filling up, precedes it in the mathematics. The output simply is, from the very first moment the object is said to exist. Physicists studying the object's structure have looked for something that functions like a fuel source and found nothing that fits. No collapsing cloud feeding it beforehand, no accretion phase, no conservation law being quietly satisfied off-screen. The energy pouring outward has no debit anywhere in its own ledger. This is different from being merely strange. Conservation of energy is one of the most stress-tested principles in all of physics, verified across chemistry, engineering, particle collisions, and stellar physics without a documented exception. A white hole, taken at face value, would be the one structure in the universe that spends without ever having earned. which is usually in physics the signal that something in the picture isn't meant to be taken at face value. It's worth understanding exactly why conservation of energy carries the weight it does, because it isn't simply a rule physicists have grown fond of through habit. In 1918, the mathematician Emmy Noether proved a result that connects every conservation law in physics to a corresponding symmetry in the underlying equations, a result now simply called Noether's theorem, and one that many physicists consider among the most elegant in the entire field. Energy conservation, in this framework, isn't an independent law bolted onto the rest of physics. It's a direct mathematical consequence of the fact that the laws of physics don't change from one moment to the next, that an experiment run today would come out the same way if run tomorrow, all else being equal. Physicists call this time translation symmetry, and it is, as far as anyone has ever measured, a genuinely deep feature of how the universe is put together. Break that symmetry, even slightly, and energy conservation goes with it. Keep it intact, and energy conservation is guaranteed, not as an empirical accident, but as a mathematical certainty. That's what makes the white holes ledger problem more than a matter of accounting. It isn't simply that nobody has found the fuel source yet, the way a detective might not yet have found a motive. It's that the very feature of spacetime that guarantees conservation of energy everywhere else in physics appears, in this one case, to produce an object that violates the thing it's supposed to guarantee. Unless something about the geometry itself is doing work that ordinary energy bookkeeping doesn't capture. And there is, in fact, a genuine subtlety here worth taking seriously, because general relativity does complicate the picture of energy conservation in ways that flat Newtonian intuition doesn't prepare you for. In a curved space-time, there's no single universally agreed upon way to define the total energy contained in the gravitational field itself, the way there is for the energy contained in matter or radiation. Physicists have developed several workable definitions that apply in specific circumstances. The ADM mass, formulated by Richard Arnowit, Stanley Deezer, and Charles Misner in 1959, which measures the total mass energy of an isolated system as seen from far away, and the Bondi mass, developed by Hermann Bondi and collaborators around the same period, which tracks how that total mass energy decreases as a system radiates gravitational waves outward. These tools let physicists confirm with real precision that energy is conserved globally even in curved spacetime, once gravitational radiation is properly accounted for. It's part of how physicists verified, decades before LIGO's first detection, that merging black holes should radiate measurable gravitational waves as they lose orbital energy. None of that subtlety rescues the white hole, though, and it's worth being precise about why. Draw a very large sphere around any conventional collapse event, a star falling into a black hole, two neutron stars spiraling together, and track the total energy crossing that sphere over the object's entire history. What you find every time in every calculation anyone has ever done is a net inward flow before the object exists, and only afterward does anything flow back out in the reduced, mass energy accounted for form of gravitational waves or Hawking radiation. The debit always precedes the credit, sphere or no sphere, ADM mass or no ADM mass. A white hole's ledger, run through the exact same accounting, has no equivalent inward flow at any point in its history, at any radius, however large the sphere. The same tools that make energy bookkeeping rigorous in curved spacetime confirm the debit is missing. They don't explain it away. The comparison to Hawking radiation is worth making directly, because it's the one place in physics where black holes themselves are known to emit. and the contrast with a white hole's emission is instructive rather than damaging to the idea that emission from compact objects is possible at all. In 1974, Stephen Hawking showed that black holes aren't perfectly black after all. Quantum effects near the horizon caused them to emit a slow, faint trickle of radiation, now called Hawking radiation, and critically, that radiation is paid for out of the black hole's own mass. As a black hole radiates, it very gradually loses mass and shrinks, evaporating over timescales that for a stellar mass black hole would dwarf the current age of the universe many times over. The emission has a debit. It's drawn down from an actual reservoir, one built up during the object's earlier collapse, and the black hole's mass visibly decreases to pay for it. A white hole's outward stream has no such shrinking reservoir behind it. It isn't spending down a stockpile built earlier. There's no earlier. The output simply exists, unfunded, from the object's very first instant. It's tempting, and physicists have tried this, to picture a white hole as something like Hawking evaporation running in reverse. Instead of a black hole slowly leaking mass outward over eons, a white hole would be radiation converging inward from every direction, across the entire remaining lifetime of the universe, arriving at a single point and assembling itself into an object that then appears to explode outward when watched forward in time. It's a tidy image, and it even has the right shape. Run the evaporation movie backward, and mass does appear to build up rather than drain away. But this is precisely the same requirement Chapter 7 already ruled out, seen from a different angle. For that inward convergence to actually happen, every photon that would ever have been part of a real black hole's Hawking radiation across the black hole's entire eons-long evaporation would need to converge on the same point in perfect reverse time coherence, with no other radiation ever interfering, the identical impossible emptiness just described in terms of a specific radiation field instead of the cosmic microwave background. It isn't a rescue for the ledger problem, it's the ledger problem, and the empty pass problem turning out to be the same demand, viewed from two different chapters of the same book. There's a broader instinct in physics this all connects to, one that shows up far outside the context of black holes and white holes. Patent offices around the world have, for over a century, maintained standing policies against even considering applications for perpetual motion machines, devices that would produce more energy than they consume, running forever without any external input. It isn't that patent examiners have personally disproven every design submitted to them. It's that the principle those designs would need to violate is one of the most thoroughly, repeatedly, catastrophically confirmed principles in the whole of physics, tested across 2 centuries of engineering failure, thermodynamic experiment, and, as Noether showed, deep mathematical necessity. A white hole, judged purely by its energy ledger, has the same shape as a perpetual motion machine. Output with no matching input, running not for a finite stretch, but from its very first instant of existence. Physicists don't reject the idea out of stubbornness. They reject it for the same reason patent offices do, because the ledger doesn't balance, and nothing about the object's structure suggests it ever could. None of this has stopped every physicist from walking away from the idea entirely. A handful have simply changed what they're imagining, trading the clean, eternal white hole of the original Schwarzschild geometry for something briefer, stranger, and, crucially, actually funded by a real collapse that happened first. That version doesn't solve the ledger problem so much as sidestep it by insisting the object only exists for an instant, borrowed directly from an ordinary black hole's own mass. Whether that sidestep actually works is the subject of the next chapter. The only version that might work doesn't last. Not every physicist has given up on the idea. A few have simply changed what they're imagining. In one proposal developed within loop quantum gravity, a framework that tries to describe gravity at the smallest possible scales, where ordinary general relativity is expected to break down, a black hole doesn't collapse forever into a true singularity. Instead, as it shrinks past a certain density, quantum effects are thought to halt the collapse and reverse it. The object bounces. What was falling inward starts moving outward again. For a moment it behaves like a white hole. Physicist Carlo Rovelli and collaborators have worked out versions of this idea in detail, sometimes calling the intermediate object a Planck star. From inside, the bounce could take almost no time at all. From outside, due to the extreme time dilation near the collapsed object, it could appear delayed by billions of years, long enough that a white hole, switching on today, could, in principle, be the late arrival of a bounce that happened almost instantly from its own perspective, long ago. Here's the part that keeps this from being the happy ending. Even in this version, nothing suggests a stable, lasting white hole. The bounce, if it happens, is thought to be brief, closer to a single sharp burst than an object you could point a telescope at for a decade. There's no proposed mechanism in this picture or any other for a white hole quietly persisting the way a black hole persists. There is no version of this where you get to visit one. There is only, possibly, a flash, gone by the time the light announcing it has finished leaving. It's worth understanding what loop quantum gravity is actually proposing, because the bounce mechanism only makes sense once you see what problem it's trying to solve. General relativity treats spacetime as smooth and continuous, infinitely divisible, the way you'd naturally picture a stretch of empty space if nobody told you otherwise. Quantum mechanics, by contrast, has spent a century teaching physicists that almost everything at small enough scales turns out to be discrete. Energy comes in packets, angular momentum comes in fixed steps, matter comes in countable particles. Loop quantum gravity, developed from the late 1980s onward by physicists including Abhay Ashtekar, Lee Smolin and Carlo Rovelli, takes that lesson and applies it to spacetime itself, proposing that space is not infinitely divisible after all, that area and volume come in discrete quantized units, built out of structures called spin networks, with a smallest meaningful length scale around the Planck length, roughly 10 to the power of minus 35 meters, a distance so far below anything any instrument has ever probed that it's closer to a theoretical flaw than a measured one. That discreteness is what does the work in halting a collapse. In ordinary general relativity, nothing stops a collapsing star from crushing itself down toward infinite density and zero volume. A true singularity, the mathematical breakdown, Chapter 2 mentioned sitting at the center of every classical black hole. But if space itself has a smallest possible grain, the way loop quantum gravity proposes, then there's a flaw beneath which density simply cannot climb any further, in the same rough sense that electron degeneracy pressure stops a white dwarf star from collapsing indefinitely, or neutron degeneracy pressure holds up a neutron star against its own gravity. Rovelli and his collaborator Francesca Vidotto worked out a version of this quantum flaw in a 2014 paper published in the European physical journal C, that gave the halted, compressed object its name, a Planck star, a knot of matter compressed down to somewhere near the Planck density, an almost incomprehensible 10 to the power of 93 grams per cubic centimetre, where quantum gravitational pressure, rather than any known nuclear or electromagnetic force, is what finally pushes back. Once collapse halts at that floor, the object doesn't simply sit there. In this picture, the same quantum pressure that stopped the crush reverses it, and the star begins expanding again, bouncing the way a compressed spring bounces back once you stop pushing on it, except the thing being compressed and released here is the geometry of spacetime itself. A companion paper by Rovelli and the physicist Hal Haggard, published in Physical Review D in 2015 under the memorable title Black Hole Fireworks, worked out how a bouncing interior like this could be mathematically glued to an ordinary black hole exterior on one side and an ordinary white hole exterior on the other, describing in effect a genuine quantum gravitational tunneling process from one geometry to the other, with the classical singularities on both ends replaced by a single, finite, non-classical transition region where quantum effects, rather than infinite curvature, govern what happens. The time dilation detail is where the proposal gets genuinely strange, and it's worth sitting with the numbers rather than just the general idea. From the collapsing object's own point of view, it's proper time, the clock that would tick on a wristwatch riding along with the collapsing matter. The bounce could be close to instantaneous, a compression and rebound happening in a fraction of a second, but gravitational time dilation near a collapsed object is severe enough that a distant observer, watching from far away, would see that same brief event stretched out enormously. For an object with a mass in the range physicists associate with primordial black holes, tiny black holes hypothesized to have formed not from stellar collapse, but from density fluctuations in the very early universe, first proposed by Stephen Hawking and Bernard Carr in a 1974 paper. The calculated time dilation factor for a bounce can come out close to 14 billion years, roughly the entire age of the universe, which means, in this framework, a primordial black hole formed in the universe's first fraction of a second could, from its own internal perspective, have already bounced almost immediately, while from our perspective, watching from outside, that bounce might only now be reaching the point where it becomes visible, its explosion arriving today as the tail end of an event that, for the object itself, finished almost as soon as it started. That detail is what turned this from a purely theoretical curiosity into something with an actual observational proposal attached to it. In a 2014 paper published in Physical Review D, Aurélien Barrau, Rovelli and Vidotto suggested that the sudden release of energy from a Planck star's bounce, a real astrophysical collapse reaching its quantum floor and rebounding, releasing whatever matter and radiation it had accumulated in a single sharp burst, might be detectable today as a fast radio burst, the class of extremely brief, extremely energetic radio flashes, typically lasting only milliseconds, that radio astronomers had been cataloguing since the first one was identified in 2007, and that remained, for years afterward, largely unexplained. The proposal predicted a specific signature, a millisecond-scale radio flash, accompanied by a shorter wavelength companion signal tied to the size of the exploding object, arriving from old, low-mass, primordial black holes finally completing bounces they began near the dawn of the universe. It's worth being honest about how that particular prediction has aged, because it cuts directly against treating this chapter as a loophole rather than a genuine narrowing of the possibilities. fast radio burst astronomy has advanced enormously since 2014, helped by dedicated instruments like the CHIME telescope in Canada, and the picture that has emerged points overwhelmingly toward a different, far less exotic explanation for the vast majority of observed bursts: magneteers, the extraordinarily magnetized remnants of massive stars undergoing violent adjustments in their intense magnetic fields. That explanation stopped being purely theoretical in April 2020, when astronomers detected a fast radio burst-like flash coming directly from a known magnetar inside our own galaxy, designated SGR 1935+2154, caught simultaneously by multiple observatories and matched precisely with an X-ray counterpart from the same object. It was the first time a source of this kind of burst had been pinned down with that level of certainty, and it strongly reinforced the magnetar explanation for the broader population of fast radio bursts observed across the universe. None of the large catalogues assembled since, including CHIME's, which has logged many thousands of events, have turned up a burst with the specific companion signal signature the Planck star proposal predicted, or any statistically compelling case for a subpopulation that fits a bounce explanation better than a magnetar one. That doesn't mean the Planck star idea has been formally disproven. Proving a negative for a rare, theoretically uncertain event buried among thousands of ordinary ones is a genuinely hard observational task, and the physicists who proposed it have always framed it as one candidate explanation among several, worth searching for rather than confirmed. But it does mean the one place this framework offered a concrete, checkable prediction has so far come back empty, in much the same shape as the searches described in Chapter 6. The theoretical mechanism remains mathematically interesting. The observational case for it actually happening has, if anything, gotten thinner as the data has gotten better. And even setting the observational question aside entirely and granting the mechanism every theoretical benefit of the doubt, the proposal was never claiming to rescue the white hole this book has been describing since Chapter 1. Loop quantum gravity itself remains an unconfirmed framework, one serious candidate among several competing approaches to quantum gravity, including string theory and various other programs, none of which has yet been experimentally verified, because the energies and length scales involved sit far beyond what any particle accelerator or precision instrument can currently probe. And even within the framework, on its own terms, nothing about the Planck star picture describes a lasting, stable, revisitable object. The bounce is explicitly modelled as brief. For realistic astrophysical masses, a burst lasting a fraction of a second is seen locally, stretched by time dilation into something that might only ever appear, from the outside, as a single instant of radio noise and then nothing more. There's no proposed follow-up phase where the object settles into anything resembling the calm, persistent, eternally open white hole geometry of the original Schwarzschild solution. It tunnels, it flashes, and, as far as the mathematics of the bounce itself describes, it's gone, its brief contact with the outside universe likely triggering the exact horizon instability described back in Chapter 4 almost as soon as it begins. So even the version of this idea taken most seriously by working physicists, published in peer-reviewed journals, attached to a genuine testable prediction, funded by an actual collapse that actually happened first, even that version doesn't produce the object this book opened with. It produces something closer to an echo of one, a flash borrowed briefly from a real black hole's own mass, visible for less time than it takes the news of it to finish arriving, and then gone, with nothing left standing where, for a fraction of a second, something else briefly was.